Operations with radical functions. So in the first question, we're going to take two functions and we are going to divide them. So first of all, I want to make sure that you understand what the question is asking. So you're just seeing an f over a g, but really it's saying take the function of f and divide it by the function of g. Another way to write this is that f over g with an x next to it. Those are equivalent, so you might see both notations. So I'm going to start by taking that function of f and rewriting it. X minus 7 is in our numerator, and in our denominator we have that g function, which is 2x squared minus 13x minus 7. I'm going to try and simplify the denominator just to see if this will cancel any further. So I'm looking for factors of 2x squared minus 13x minus 7. So that actually simplifies to be 2x plus 1 and x minus 7. So you'll notice that we actually have two terms in the numerator and the denominator that are the same, so they can cancel. So the final answer is 1 over 2x plus 1. We also have to take into account what the domain is. Because we have a denominator, we want to make sure that the denominator cannot equal 0. So we're going to set our denominator equal to 0 and solve. So 2x plus 1 is equal to 0. And x is equal to negative 1 over 2. What we actually found is what x cannot equal, because if x does equal negative 1 over 2, we would get a 0 in the denominator, which would make the entire function undefined. Even though the x minus 7 canceled out, at one point it was part of the denominator. So we actually have to find our domain restriction for that too. So x can also not equal 7. So we're finding out what the factors in the denominator equal, so we can actually say that in our final answer, our domain, our x cannot equal those two numbers. So we need this entire thing as our solution. In example 4, we actually have a composite function where we're putting one function inside of another function. So the g function is going inside of the f function. So we're going to actually start with that innermost function. We're going to find g of 3. So normally there's an x here, and the x has been replaced with a 3. So we will go and use our g function, which is x plus 1, and we're going to change the x to equal 3. So we get 4. So then what we've done is we've actually replaced, because we just found that g of 3 is equal to 4. So we're going to replace g of 3 with the number 4. And so now our question is, using the function of f, replace the x values with 4. So our f function is x squared. We're going to replace the x with a 4. So we end up getting 16. The rule is start with the inside function and simplify out. In our next example, we also have a composite function, meaning that we have one function inside of the other one. The difference with this question is you'll notice that there is still an x with that g function rather than a number. That's okay. All we're going to do is we're going to take our g function and we are going to put it inside of our f function. So g of x is equal to x plus 1. Now the question is saying find f of g of x. So what we're going to do is we're going to take g of x and we're going to replace it. Well, if g of x is equal to that x plus 1, we're going to put that inside of f. So we get f of x plus 1. So our original f function is equal to x squared. So what that means is we are going to replace x with x plus 1. Whatever we do on one side of the equation, we have to do on the other side. So we're going to simplify by foiling. We get x squared plus 2x plus 1. Now this question isn't asking to find the domain, but later on we are going to learn more about domains. When you find the domain of a composite function, you look at the domain of the inside function and the domain of the solution. Let's go back and look at the original question. The domain of the inside, x plus 1 is a linear, so our domain for this is all real numbers, and our domain for our answer is x squared plus 2x plus 1. So our domain for a quadratic is negative infinity to infinity as well. Since the inside function and the domain of the composite function are identical, then it satisfies our question as our overall domain.